All right, let's get this show on the road. Hello, everyone. Thought I saw a flyer or something. I just opened the window. It's very nice outside, but here we are doing calculus because, it's awesome. All right, so we had our first quiz today. Hopefully you guys did okay on that. Seems like there were some technical issues, which, I mean, it's the first time we're doing it on a new platform, so that is to be expected. What I would say is if you were unable to upload your work through Gradescope, which is what we're doing, you can email it to me right now, like within the next 2 minutes before, or it's not going to be accepted. Make sure you use my email on the syllabus. So that's Jhevon. Well, you guys know it's the email is on the syllabus. So don't use my CCNY email. Yeah, it's seems to be short on time. I see some people talking. Okay, we'll see. All right, I'll see how the grades are. We'll see how it went. But yeah, I mean, it's the first quiz, so we'll see how it goes. If you actually were able to upload it on Gradescope, there's no need to email it to me because I can get the file from there. But if you have not done that, we'll try. You can email it to me this time only, and then we'll try to figure out something for next time. Okay. It's preferable that you type in your answers. So if you learn to do LaTeX, you can type that in, but if not, just type your answers. Which, yes, it's slightly annoying, but it should be doable either way. Anyway, let's get this thing shared. I also have an announcement to make today. Let's see if I can remember that. Okay, so yes, those are the right notes. All right. So I'll see how the quizzes were this time around, and then we'll correct for next time. Let me turn off the video here. So yeah, it's preferred that you enter your answers in the thing. It's better for everyone involved because that way it can auto grade, and so the grades will be faster. The email on the syllabus. Okay, all right. So last time we spoke about trig integrals. Let's actually just jump into it. Oh, I don't know. Some people had trouble. I don't think for anything you had to write out the integral of something like that. So the answer should just be functions. So you should only have to type functions for the answers or numbers this time around. Anyway, we ran a trial. I'll see how the results are and we'll correct for next time. Right now, let's just actually get into the topic at hand because, of course, we have another. Yes, you upload your answers to Gradescope. So the last question in the quiz was a question that said, upload all your work. In which case you scan it. I think the fastest way to do it is with your phone and then just enter it in. You're not going to be able to do it now because the quiz is closed. All right, so last time we spoke about trig integrals, we did a bunch of techniques. There was one example left to do. Before we get that, I had some typos from last time. Where did I put this? Okay, so last class, example D in example 7, part D. So it seems here when I was just writing down some general formulas, I didn't put in the double angles here in example 7 part D. So there were some factors of 2's missing. And so the answers, I think, should look like this. So make sure to correct that in your notes. I'll actually also repost the PDF, and so you can see these corrections here. But Jason passed it. Jason emailed me. We set up an office hours, and he mentioned that I had this typo. So what I'll do, I'll give him an extra point for this quiz for paying extra attention. Also, okay. But that's important that you can do that. If you have your notes right now, you can correct it, but I'll also correct it in the PDF. So that was the first announcement I wanted to make. The second announcement, don't want to make it now before this. And for lots of the questions were formulas. So no, I don't really think that's too many questions for a quiz. There were some that you should be able to just look at them and know the answer. About 10 of the problems were like that. There were really only 4 problems that he had to do that would take a long time. And one of the questions was actually the upload question. So it doesn't really, technically it's not counting. Anyway, let's actually just jump into it. So I'll see all these comments from the quiz, and then anyway. And as far as scanning and all that other stuff goes, that's why I put the practice quiz, so you'd know how long it will take and all that good stuff. So at some point, like some of these complaints are things that you should have mentioned to me before. Anyway, let's jump into this question. We'll deal with all the other issues later. How about we just do this just to remind ourselves how secants and tangents work, and we'll jump into a new topic. Hello?
Can I answer the question, or?
Yes.
Okay.
Yes, let's actually start.
Okay, so for the tangent squared, you would use the Pythagorean identity, and then change it to secant square minus 1.
Yeah, then?
Then you would distribute.
Sounds a minute. Okay, so this here gives you secant cubed x minus secant x.
And then from there you would use the memorized ones.
Right, and both of these you would have the forms memorized. So at this point, once we did the previous example, we learned secant cubed, told you that should be a basic rule. That's something you should have memorized. I believe I asked it on the quiz as well. So this is 1/2 secant x tangent x plus ln, absolute value, secant x plus tangent x. And then the integral of the secant, that's also something you have to have memorized. So this was minus, so this is 1/2. Minus integral of secant was ln of secant x plus tangent x plus c. And then these guys we can combine, right? These two here are the same. And so we would have 1/2 secant x tangent x. Here we have plus 1/2 this, minus 1/2 that, so it becomes minus 1/2 ln of secant x plus tan x plus c. And that would be that guy. Why wouldn't you use case 2 where you, so I have a question here. Why wouldn't you use case 2 where you save a secant tangent? Well, if I had saved a secant tangent, what would have happened? The integral would have looked like tangent times secant tangent. Now remember, when the purpose of doing that is you would want to have a secant left over so that when you do u equals secant, you get the du is secant tangent. But as you can see here, that would not have happened, right? So you can't do that. That didn't help. And case 2 says, how was case 2 phrased? Case 2, right, so remember what case 2 is. Where did I put case 2? N is odd, right? So that means the power of tangent is odd, especially when secant is visibly present. And remember, secants and tangents, they're kind of weird. But here you'll notice that is not case 2 because the power of tangent is even. So that's another situation. So there are a couple of reasons why. So you wouldn't really think case 2 because the power of tangent is even, as well as realizing that when you save a secant tangent, the point of doing that is that you want to do a substitution of u equals secant, and so your du is going to be that secant tangent. In this situation, that would not have helped. So that's this here. That being said, now I want to do, hopefully that was clear. Now I want to do an important announcement. So I'm going to make official times for office hours. So before it was just by appointment, but here I'm going to actually designate 2 hours for the class. And so I would say Mondays and Thursdays. So at the beginning of the week and at the end of the week, we'll have office hours. And we'll do this the hour before class, I think. So 5 p.m. to 6 p.m. So that's an important announcement. So usually we don't really have official office hours in the summers, but the math department said, you know, considering everything that's going on, we're actually going to require you guys to hold official office hours, and of course we're going to compensate you for that. The office hours will be through Zoom, and if you want to see me during office hours, because it's a security risk actually posting the link in public, just email me, tell me that you want to meet during office hours. I will be around my computer, and then I'll just send you the link right away. Okay, but just know that I will be available during the hour before class on Mondays and Thursdays. And so if you want to actually reach out to me, ask me anything, have office hours, those are the official times. Now, if you still want to see me during office hours, you have any other issues, of course, email me and we'll set up some other time. But these are quote unquote official times. So unless some sort of emergency happens, I'm guaranteed to be available during these 2 times. I've written you guys into my schedule. So yes. All right. So, and hopefully as we move forward, you know, this is a learning experience for everybody. We'll sort of be able to get things more streamlined. Yes, and I do appreciate that doing a quiz online, typing answers as well as scanning things, it's kind of annoying. But we're going to have to kind of learn to do that, and I'm going to have to learn to make sure to give an appropriate amount of time for this to happen. So the thing is, it's really important for you guys to be able to write out your work. So I don't want to give you a quiz where you only have to enter the answers online and you don't show your work. Also, you can just use an online calculator and do the answers. And so there's no real way for me to check that you actually did the work, as opposed to just use Wolfram Alpha. So it's important for me to see your work for a variety of reasons. Also, it also helps me to give you partial credit. So you can even look at it that way. So if you just write down an answer and your answer is wrong, then okay, now you just got the problem wrong. There's nothing I can do about it. However, if you've got the answer wrong, but then I look at your work and I realize, oh, this 90% of the problem, but they just messed up in this one step right here, that allows me to give you partial credit for the problem. So full written out work is important to me because it tells me that you didn't just plug anything in the calculator, but it's also important to you because now you have some way to get partial credit on tests. Now, overall on quizzes, partial credit is harder to come by, but in general, for tests, you will get partial credit. And this is going to be a way for me to find that, to be able to apply that. Okay, so those are my official office hours. Send me an email and I'll send you the link to a Zoom room where we'll meet. If you have any issues otherwise, you can still send me an email and we'll try to find a time that works for both our schedule. But hopefully the hour before class is good for most, if not everyone. So those are the two main announcements I wanted to make. So one announcement was the typo in example 7 part D from the last class, which Jason was so kind to point out to me. And the second is official office hours. So you can reach out to me if you ever need anything. And yes, I have heard everything you guys said about the quiz. We will go through and we'll fix it. But I just want to see what the grades were for this quiz this time around, and I can compare it to previous semesters and see how you guys went. I'm very optimistic. Let's go. All right. So that was the last example. We are going to move on to so as for the office hours link, it will, I think more than likely I will leave it reoccurring. However, I would still want you to email me. Yeah, whenever, okay, so let me answer one question at a time because there are a couple questions coming in. So the Zoom hours for office hours, the Zoom link for office hours, I think will be reoccurring. The thing is I still want you to email me though, because I probably won't leave Zoom running on my computer because for some reason my computer gets hot when I just leave Zoom running. So I'll probably not have it running, but the moment you email me and say, hey, I'd like you to meet me for Zoom, then in like 30 seconds, I'll be able to be on Zoom. To answer the second question, yes, anything that has a double star, I expect you to have it memorized as a basic rule. And so you do not have to actually show the work of how you got there. So for example, for the integral of secant cubed, you don't have to derive that every time. Or the integral of ln x, I don't expect you to derive that every time. For now, that's a basic rule. At any point, you can just write in the answer for that and it will be fine. So anything that was double asterisk or anything that I said, okay, this is a basic rule for you guys, then you do not have to show the derivation of that. You can just give me the answer. I will not consider that cheating or not showing your work or anything like that. So yeah, so if it showed up on a quiz, you can just write in the answer, no work necessary for anything of that sort. So I believe I put secant cubed on the quiz today. I didn't expect you guys to actually take the time to write all that out. So if a lot of you are running out of time because you're showing work for literally everything, then that's probably the culprit. So the first 10 problems on the quiz today, you weren't supposed to show any work. It was just like complete the rule. So you weren't supposed to be actually working things out. Those were guys that I expected you should look at them, know the answer, write them down. So if that was the issue, then yes, I completely agree with you. It wasn't enough time, but that wasn't the issue. If you read the question, I would say just complete the rule, fill in the blank, right? So the first 10 problems of the quiz, you shouldn't be showing any work. If you showed work for all 17 items on the quiz, then yes, that was not enough time. You had to show work for literally 4 items on that entire quiz. There were 4 problems that you had to write out full solutions. Everything else, you could have just written down the answers. Okay, so this is a learning curve. Now you guys know. When it comes to quizzes, I always test you first on rules, basic principles. These are things that I just expect you to regurgitate. Just remember, write them down. And then I will also give you problems where you have to actually show some work. So that might have been the issue. And so, yeah, now we know for next time. Yeah, just fill in the, yeah. I could have, but I thought it was obvious when I said just fill in the rules. This, like I said, it's a learning curve for both of us. I did, yes, I did say thank you, Natalie, for coming to my defense. I did send that in an email before. Yeah, now I just remember. I normally don't announce what I'm going to put on a quiz, but I did send in an email. Hey, this is the quiz. There are going to be 10 problems where it's just the rules for you to put down. Then there are going to be 4 integral problems. Then there are going to be a couple bonus problems. I did say that. So yeah, basic rules, you don't have to show work. These are just things I want you guys to know. And you can just write down the answers at any time. Don't show any work, it's fine. So if I say complete the rule, I literally mean just fill in the blank. If I say evaluate the integral, that's different. That's something like you have to do a problem now. You have to work out and evaluate the integral. Okay. All right, we're all learning here. So let's try to make note to selves and do better next time. So completely this, so for quizzes, it's usually like 1 point per problem. So so it'll be about 14 points for this quiz. So there were 10 problems where you had to just fill in the rule, and then there were 4 problems that you had to write things out. So the quiz just counts for 14 points. Then you had bonus problems. Those were optional. You didn't have to do them, but that could give you 2 extra points. And then there was the last question was the upload question, which doesn't really count for anything. It's just you uploading, showing your work. Okay. All right, so we don't have much time, so let's actually get into the matter at hand, what I want to talk about today. For the most part, there's nothing much for me to teach you here, but to actually apply the knowledge, it's going to take some practice for us to get through. We're going to talk about trig substitution. So let's actually just jump into that. Hopefully I can finish most of that today so that we don't have to do much, if anything, for trig substitution tomorrow. So here's the intro. Substitution is a lot broader than Calc 1 students tend to believe. Normally, when you think of substitution, students think that, okay, I'm just going to set u equals some expression that I'm looking at in the integral, and then finding my du and substituting all of these guys is going to turn my integral into something much simpler. The thing is, sometimes you can change your substitution and you can make it a little bit more robust. You can make it a little bit more convenient. It's not just a straight up, oh, set u equals this or set t equals this that I can look at. Sometimes you can actually cater your substitution to deal with the problem at hand. So here's an example. And I think there was a similar one to this on the quiz. And so I'm going to show you guys a couple ways to actually do something like this. So here's the typical way that a student will do it, typical Calc 1 student. Right, so they'll see the integral of x cubed over the square root of x squared plus 1, right? And then they'll say, okay, a substitution can work here, right? And they'd be correct, a substitution can work here. So they'd do something like, okay, set u equals x squared plus 1. Then that means your du would be 2x dx. And that means that 1/2 du is going to be x dx. And then they're going to realize something like, oh, well, this here, the x cubed, I can think of the x cubed as x squared times x. And so this x dx here is that x dx there. And then because u is equal to x squared plus 1, this means that my x squared, I can replace that with u minus 1. And then this here is u. And so you can go in and you can actually plug in this substitution. And so where you saw x squared, you're going to put u minus 1. Where you saw the x dx, you're going to put 1/2 du. And where you saw the u, you're going to put, where you saw the x squared minus x squared plus 1, you're going to put u. Ultimately, you'll see that integral breaks down into, well, 1/2 times u over radical u minus 1 over radical u du. Then you can rewrite that using laws of exponents. This is u to the 1 divided by u to the 1/2. So you subtract the powers, this gives you u to the 1/2. This is u to the minus 1/2. And so now you can integrate this, add 1 to the power, get 3/2, divide by the new power, 2/3, minus add 1 to the power, you get 1/2, divide by the new power, 2, plus c. And so now you would end up with 1/3 x squared plus 1 to the 3 over 2 minus x squared plus 1 to the 1/2 plus c. And that would be how a student would go through it. Okay, so that's nothing strange. Here's another way to look at this same problem, okay? So we haven't really learned anything new here. Here's another way to look at it. So here I have the integral of x cubed over the square root of x squared plus 1. That was the guy. But here's the thing. I'm not just going to do the old Calc 1 brain dead substitution, u equals x squared plus 1. What I can do here is do the following. I'm going to set u squared equals x squared plus 1. So here I'm taking the normal everyday substitution, but I'm tweaking it a little bit. Why? Because it's more convenient. Because you see there's a radical here. So if I put a square under the radical, they're going to cancel out, right? And that's going to help me, right? So here, notice now I can actually do the substitution. 2u du is equal to 2x dx. And so you get u du is equal to x dx. Of course, from this, you also realize that your x squared is actually going to be u squared minus 1. And so what do you notice is going to happen here? This integral here, which looks like x squared times x dx over the square root of x squared plus 1. Now when I start to actually plug in my substitutions, look what's going to happen, right? So it's the same integral, very similar substitution, but I tweaked it a little bit. I tweaked it in such a way that the radical, I'm actually going to get rid of the radical. Now, notice here that this x dx is going to become u du. This x squared is going to become u squared minus 1. And then this entire thing, including the radical, is going to become u, right? Because I'd have the square root of u squared. Technically, it's the absolute value of u, but what's underneath the radical is always positive, so it works out to be the same. Now, if you plug this in, what is that going to look like? This is going to look like u squared minus 1 times u du divided by u. Your u's are going to cancel. And look at this integral, the integral of u squared minus 1. Now, compare this integral here. Compare that to like this integral here. So when I finish the regular substitution, I get this, which I had to convert to this, I had to transform and have radicals in the powers, and here it's a square root, so it's not that bad. The half power we're very used to dealing with, but you can already see if the function was a little bit more complicated and the radical wasn't a square root, but it was some other strange radical, you can already see that the arithmetic is going to start getting annoying here. Whereas by doing this small tweak with our substitution, I could take advantage of how the integrand looks to be able to get a simpler integral to deal with at the end of the day. So I tweak my regular old substitution to get something a lot nicer. At this point, it's just the power rule, and I'm doing it with integers. It's super easy. And now I can plug in the, what this guy was. This was x squared plus 1 to the half, so that becomes 3 halves, over 3, minus x squared plus 1 to the 1/2 plus c. And that's, I get to the same answer, as you can see. I get to the same answer. However, the journey along that answer was a lot nicer because of a little tweak to my substitution. Okay, so there is some benefit to actually thinking of your substitution in a little bit broader sense, a little bit more generally. So for example, if this was, so another example. Given if I had something similar like x cubed over the cube root of x squared plus 1 dx, then u cubed equals x squared plus 1 would be nice. Right? So I can actually change, I can modify my substitution to play nicer with the integrand at hand. And this can make your life a lot easier. Now, beyond making your life a lot easier, there are situations in which, without modifying your substitution to be a little bit more robust, it can actually go from, you can actually be in a situation where trying to do a regular substitution is pretty much impossible to pull it off. However, by tweaking the substitution, it becomes possible for you to do the integral. So sometimes it's a matter of convenience and it's kind of optional. Here's a situation where I can do a regular substitution, use substitution in the sense that a Calc-1 thinks about it, but I can make my life a little bit easier by just modifying the substitution a bit. There are times when modifying a substitution is literally the difference between being able to compute the integral and not. Oh, the 2u du came from the derivative. Remember how substitution works. You come up with a substitution equation and then you differentiate that equation. The derivative of u squared is 2u. Right, so that's where the 2u came from. So you differentiate both sides. This is 2u du by the chain rule. This will be 2x dx by the chain rule. All right. But hopefully that gives you some appreciation for how tweaking a substitution can change things. Now, there are times, as I'm going to show you, where it's literally impossible for you to figure out something without tweaking your substitution. One of the most important scenarios in which this comes up is trig substitution. So there's something called trig substitution. So this is when we're going to tweak our substitution to involve trig functions, everyone's favorite kinds of functions, right? So that's what we're basically going to be able to do. Now, we know that the following is the case. Okay, so at this point, we have someone else joining here. Okay, so here are some identities. Nothing new here. We all know what these identities are, right? We all know that 1 minus sine squared is cosine squared, 1 plus tangent squared is secant squared minus 1 is tangent squared, okay? So these are identities that we know. Notice that if I multiply both sides of the equation here by a squared, I can write the equation as this, right? A is just some constant. Okay, let me write that. A equals some non-zero constant. Right? So starting with a trig identity, I can multiply both sides by a squared, multiply by a squared, to rewrite the equations in this form. So that's nothing new. I took an identity and I multiplied both sides by a squared. Now what you realize is that if I would take this inside function here, like the a sine theta, and I think of that as some variable, call it x. Essentially what this means is that I can think of the expression a minus x squared as this cosine expression. Now, why this is nice, notice that over here, I have two terms, while over here, I have one term. Now, there are situations where this can be very, very convenient. For example, when I'm under a radical, right? If I'm taking the radical of a sum of terms, this is very complicated. We actually don't know how to simplify that. Very annoying to deal with. However, if I have one term under a radical, then I raise it to a half power. It's a lot easier to deal with. Okay, I can actually write that a little bit nicer. So by looking at, you can look at these trig identities as a way to go from a situation where we have two terms to a situation where we have one term. And we are going to take advantage of this pattern. How can we take advantage of this pattern? Well, this leads to the following table. Okay. So this means whenever I see an expression like a squared minus x squared, I can think of the x as if it were an a sine theta, right? And that is going to allow me to combine things, right? Notice that this means that a squared minus x squared is going to become a squared cosine squared theta. So I can go from a situation where there are two terms to a situation where there is this one term, okay? Now, I'm just using what I used in the table up here, so hopefully that's not confusing anybody, but you'll see this when we actually put it all together. Here's something else that we have from this situation. Well, if my x is a sine theta, this would mean that my x divided by a is sine theta. This would mean I am able to draw a right triangle at this point, where the opposite is x and the hypotenuse is a. Of course, this would mean that this side here is a squared minus x squared, which you'll notice is from the original expression over here. So I'll be able to come up with that. Similarly, if I have a squared plus x squared, this reminds me of this identity here. And so I can think of my x as a tangent, right? We're going to see how this fits together pretty soon, right? This would mean, of course, that my x divided by a is tangent theta. And of course, this means I can draw a right triangle, where the opposite is x, the adjacent is a, because tangent is opposite over adjacent. And so the hypotenuse would be the square root of a squared plus x squared. There you see the a squared plus x squared, again, that expression from the original. Similarly, if I have x squared minus a squared, this reminds me of secant squared minus 1. And so I can think of my x as a secant. This would mean that my x over a is equal to secant theta. So this means I'd be able to think of a triangle. And secant, remember, secant is 1 over cosine, and cosine is adjacent over hypotenuse. So this is hypotenuse over adjacent. And so the opposite would be x squared minus a squared square rooted. Okay. So these guys here, these are called trig substitutions. In other words, there are going to be times when I'm going to have an integral, and I'm going to see an expression that looks like this: a squared minus x squared, a squared plus x squared, or x squared minus a squared. And I'm going to substitute into the x a trig function. What trig function? Well, this specific trig function. Whenever I see this scenario, I substitute a sine theta. It's also worth mentioning that it's not traditional, but notice that x equals a cosine theta would also work. But we usually don't do that because that guy gives a negative sign. But whenever I see an expression like a squared minus x squared, I can replace the x with a sine function. This sine function specifically, a sine theta, where a squared is the constant term. This will allow me to take advantage of this diagram. It will also allow me to take those two terms, a squared minus x squared, and turn it into one term, a squared cosine squared. And in these there are three main scenarios that we want to learn here. So this is a squared minus x squared, a squared plus x squared, and x squared minus a squared. If I see any of these three expressions in an integral, then I have the option of doing this kind of substitution. It's called a trig substitution. It allows me to combine two terms into one. It also allows me to take advantage of this diagram here. All right. So again, this here, these tables, these are just things that you should know, right? So you should know if I see this, I have the option of this substitution. If I see this, I have the option of this substitution. If I see this, I have the option of that substitution, etc. Okay. So now, hopefully that is clear. So nothing new here, just trig identities. We just want to look at them in a different way. Yeah. Is there a question? Someone turn their mic on, I guess. Mute yourself unless you have a question. Okay. All right. So far, hopefully so good. Now, some of you might be wondering, where are you going with this? Okay, let me actually show you an example of where we can apply this. So here are some examples. We're going to go through all these examples. And you're going to see how we're going to apply this idea. Now, these examples, you will notice, they're a little bit tough to deal with any technique that we've used before. But with the above substitutions in the table, you're going to realize that, now suddenly I can actually do the integral. There's one other thing that I would say is very important to know here, even though strictly speaking, it's not necessarily a part of the method, it's a recommendation. Back in Calc 1, when you were learning substitution and you had a definite integral, you guys would have learned that you kind of have the option to change the limits on your integral or not change the limits. Now, my recommendation is whenever doing a definite integral, that is the integral with the numbers on it, using a trig substitution, always change the limits. Now you're going to see why I make this recommendation pretty soon. I have an example here where I'm doing a definite integral. This example G, we're going to do that and I'm going to show you why I made this recommendation. So it's not a part of the method, but it's going to be very convenient. Okay, so what we need to know for this section is this table. So you need to know this table right here. So double asterisk on the whole table. So you should know whenever you see an expression like a squared minus x squared, you can substitute x equals a sine theta. Whenever you see a squared plus x squared, you can substitute a tangent theta. Whenever you see x squared minus a squared, you can substitute a secant theta. At this point, I'll pause a little bit because I want you guys to take a screenshot of this. Now, I know you're not going to have it memorized right now, but while we're going through these examples, if you have to look at your screenshot to see what substitution to use, it's okay, you can do that. But I'm going to be asking for your input eventually, and so I want you guys to have like all those substitutions. So, okay. I'm pausing for 5, 4, 3, 2, 1. Okay, so hopefully you took a screenshot of this table, right? So the important thing is when you see these expressions, you can make these substitutions. Now, I'm going to go through this example slowly on my own. And you guys are gonna watch me do this example. If you have any questions, you can ask me about it. And then what we're gonna do is you guys are going to help me do all the other examples, which I don't think we'll get through all of them today, but eventually we'll get through. Okay, so try to pay attention. Now, here's an integral. This is an integral. Now, remember, I remember my training grasshopper. Okay, so whenever I see an integral, the first thing I look for is this a basic rule? And the answer is no. Can I simplify it to get a basic rule? The answer is no. And the issue is that there are two things in the radical in the denominator. Can't really simplify those guys, at least not in any way that's going to be much simpler. So no, can't really do step 2 of my integral strategy. 3, can a substitution work? Now, this might be something that someone would have thought. Can I do a substitution here? Now, what would you substitute? It seems that the obvious substitution would be to do u equals 4 minus x squared. However, you're going to notice that your du is going to be minus 2x dx. Then you're going to realize that minus 1/2 du is equal to x dx. This guy here is going to be x times x dx. And so now when you start to plug in the substitution, what you're going to get is your x is going to become what? Well, if I were to solve for x here, I would get 4 minus u and then square rooted. Now, of course, there's going to be a plus or minus. That's already kind of annoying to deal with, but whatever. Let's continue. The 4 minus x squared is just u, which means on the bottom, I have radical u. In the top, the x dx is going to be that minus 1/2 du. And so now you realize you'll have this integral here. Now, it turns out that that's complicated. Right? It's actually no better than the original. I mean, how would you integrate that? Like, what would you even do? Right? Like, there's nothing to do here, right? Radical of 4 minus u over radical u, like, how are you going to integrate that, right? So it turns out that substitution is not going to, at least a regular substitution, isn't really going to get you somewhere to the answer. Okay, so that's just some motivation for why I'm even teaching you this. So here's an integral where going through my strategy doesn't really yield any nice results, at least by substitution. And integration by parts, forget it. Come on, what are the parts going to be? Okay. Integration by parts, you could probably set one of the parts to be x, set the other part to be x over the radical of 4 minus x squared. But you'll realize that by applying that, it's also going to get more complicated than it has to be, if you can even get to an answer at all. Okay, so there is a need for a different method here, or at least there's a strong desire for one. Okay, so that being said, let's actually just jump into it. I'm rambling. Okay, so here's what I'm going to notice. Notice, now you're not really going to write this all the time, but I just want you to know what I'm thinking. 4 minus x squared is 2 squared minus x squared. This I can think of as an a squared minus x squared. You see, where a equals 2. So here I've singled out this expression here. Let me make this a little bit bigger. Hopefully you guys can see this. So if I single out this expression here, the 4 minus x squared, notice that that looks like an a squared minus x squared, which I'm primed it from memorizing this table to look for an expression like that, a squared minus x squared. Now I realize, okay, this thing here looks like an a squared minus x squared. A regular substitution isn't going to work, so maybe a trig substitution can help me. What is the trig substitution? Well, it's a sine theta, right? In this case, a is 2. So here what I would do is I would do a substitution. X equals 2 sine theta. Okay, so this is my trig substitution. Now, as always, when it comes to substitution, once you find out something that you want to substitute, you're going to have to start differentiating because you are going to have to find the differentials. This means if I differentiate it, dx is going to be 2 cosine theta d theta. Now, of course, now I can start to actually plug things in. This means that this green part here, x equals 2 sine theta, that means that this green part here is going to become, well, 2 squared cosine squared theta. Why? Well, by this table. Right? And I mean, you can actually write this out. You'd have 4 minus 4 sine squared here. You can factor out a common 4. 1 minus sine squared gives you cosine squared. So you can take a little bit extra time. So the denominator here is going to become 4 cosine squared theta under the radical. My x squared, well, that's just going to become 4 sine squared theta. And my dx, so here's my dx. That guy is now going to become 2 cosine theta d theta. So now when I plug in all my substitutions, look at what's going to happen. Here, now I'm going to have x squared. Now my x squared is just going to be 4 sine squared theta times my dx. My dx is going to be 2 cosine theta d theta divided by now under here I have 4 minus x squared, but my x is 2 sine theta, so this is 4 minus 4 sine squared. Factor out the 4, I get 4 times 1 minus sine squared, so this becomes 4 cosine squared. So I just said in words how I got the 4 cosine squared, because this substitution gives me that if my x is 2 sine theta, then 4 minus x squared is going to become 4 minus 4 sine squared. This is going to be 4 times 1 minus sine squared. This is going to be 4 times cosine squared. So yeah, so it's from what we know about trig identities, right? So this is the whole point of this substitution. We're making this trig substitution to take advantage of these trig identities. All right, now what's going to happen? Let's clean this guy up a little bit. So here we have 4 sine squared times 2 cosine times this. Now this, of course, this radical is going to cancel into the 4. It's going to become 2, and it's going to kill that square. So here, notice that I have 4 sine squared, and I'm writing this out extra long. You won't have to write out all these steps in practice, but just to make sure that we're not losing anyone. So the denominator is going to simplify to 2 cosine theta. That allows me to cancel that. And so this would become just the integral of 4 times the integral of sine squared theta. And look at that. Started out with this integral, which looks very, very complicated, right? The integral of x squared over the radical of 4 minus x squared, right? Tough to do with regular substitution or any of the other techniques we have so far. However, by doing this substitution, x equals 2 sine theta, notice that I now obtain this as the integral I have to do. Now that one we should know how to do by now. So here I would just apply the half angle formula, or the double angle formula, whatever you want to think of it. This is 1 minus cosine 2 theta. And then I can integrate that easily. So this is 2 times the integral of 1 is theta minus 1/2 sine 2 theta. Okay, so that's the answer. It's a pretty easy integral to do for in the theta universe. So I did a trig substitution, translate everything to the variable theta, and the integral is easy to do as a trig integral in theta. This is why it's called a trig substitution. You're in a situation where there were no trig functions, and you introduce a trig function so that you can take advantage of trig identities to make the integral easier to deal with. Now, because we're good with trig integrals, because we did the last section on trig integrals on Thursday, we now know how to integrate this guy easily. Now, here is, no, so in general, I'm moving very slowly now because we're learning this for the first time, but you should be able to do this relatively quickly eventually. That being said, I will mention that in general, doing an integral by trig substitution is a very lengthy process. It's going to be one of the longer type of integration problems that you do, a problem that you have to do trig substitution for, which is why I recommended that for definite integrals, changing the limits, because we are actually not done. Now, the answer you'll notice is in theta. However, the question was asked in terms of the variable x, which means we need to be able to translate this answer back to the answer x. And so now we're going to have to do the back substitution. And here's the thing with trig substitution. The back substitution process is actually pretty annoying. And this is where this part of the table comes in handy. This part of the table with the diagram from this triangle, that's going to help us with the back substitution. Okay, so now we have to back substitute. We need to find out what is the answer in x's. Okay, now we know x is equal to 2 sine theta. This means that x over 2 is equal to sine theta. This means I can draw this right triangle. This is opposite over hypotenuse. And then the adjacent side is going to be 4 minus x squared by Pythagoras' theorem. You will notice here that this means that your cosine of theta is going to be adjacent over hypotenuse. Now this means, what does this all mean? What does it all mean, Basil? Okay, so first of all, x over 2 is equal to sine theta means that your theta is going to be sine inverse of x over 2. So that's the first thing. Okay, so that's how I'm going to rewrite the theta in my answer. Okay, so that's the first thing. Now you want to know, well, how am I going to rewrite the sine 2 theta? Here's how we're going to rewrite the sine 2 theta. Again, with trig identities, 1/2 sine 2 theta is actually equal to sine theta times cosine theta. Because I know the trig identity, the double angle formula for sine, right? So this means my sine theta is going to be x over 2, which I have from here. My cosine theta, I just found over here by Pythagoras' theorem, this is going to be the radical of 4 minus x squared over 2. And so it turns out that this guy, the 1/2 sine 2 theta, I can think of that as x over 4 times this. And so, finally, the integral of x squared over the radical of 4 minus x squared is, drum roll, 2 times theta, which in this case, it's going to be 2 times sine inverse of x over 2 minus 1/2 sine 2 theta, but 1/2 sine 2 theta is this guy, x over 4 times that. Plus c. And now we're done. Yes. That took forever. That's the nature of the beast. Also why I recommend changing limits for definite integrals. Because if I change the limits, I do not need to do the back substitution, right? So you don't want to have to waste time doing all this work here if you don't have to. And if you have a definite integral, then you don't have to do all that work there. You can just change the new limits on your integral to be in terms of thetas. And so once you get to the answer in terms of thetas, you just plug them in right here, right? That way, you can plug numbers into theta, and there is no need to back substitute. Okay? All right. So let's actually recap, make sure that we all understand, or we have some semblance of what this thing actually looks like, what this process actually looks like. And then we'll do a bunch of examples, okay? So I have this integral here. I kind of marked up the answer there. Maybe I can move this. Did that actually move everyone down? Okay. So here is the example. Boom. Never mind. Okay, so you have this guy. Oh, is that for the group study? Okay, yeah, so that's a repost and a link. Okay, so here's an example. Here's the guy. I noticed the expression 4 minus x squared. Of course, remember, I do go through the whole process in my head. Is it a basic rule? Can I simplify to be a basic rule? Can a substitution work? Can integration by parts work? Or what would even the parts be? All the methods that we had before, they are not viable or not something I want to chase here. So then I start to realize, well, what other thing I can do? Well, I see the 4 minus x squared and I realize, hey, that looks like a trig substitution. I can think of that as a square minus x squared. The appropriate substitution based on this table that I have memorized, that Jhevon told me to memorize, is to use x equals 2 sine theta. Once I find x, I can find dx, and then I can plug everyone in. It allows me to simplify the 4 minus x squared into a single cosine using trig identities. Once I plug in all my substitution, everything reduces to a trig integral. Now we covered all the cases that you need to know for trig integrals in the last section. So hopefully once you get here, you should be able to get to the answer. Now, if you have a definite integral, I would transform the numbers into thetas and plug those numbers into here to apply the fundamental theorem of calculus. If, however, it's not a definite integral, then you have to find the answer in terms of x's. How do we do that? Well, our trig substitution allows us to draw this triangle, which allows me to find all the other trig functions using SOHCAHTOA. Once I find all the other trig functions using SOHCAHTOA, I can change any of the answers here in terms of theta into answers of x by applying the SOHCAHTOA. Then I end up with the final answer. Okay. Whew. Let's try again. Now this one is easy. Now this one, by the way, is a problem that you guys actually already know the answer to. Okay, now this you should know the answer by heart.
Tangent inverse tangent.
Right, that's the inverse tangent plus c. Now let's say hell freezes over and for some reason you forgot that. let's actually derive that this is going to be the inverse tangent. Okay, so here I see, okay, 1 over 1 plus x squared. I realize that here I can think of this as a squared plus x squared, where a equals 1. So then I can use x equals a tangent theta. My dx is going to be secant squared theta d theta. Of course, this is going to mean that 1 plus x squared is going to be 1 plus tan squared, which is going to be secant squared. That's why I want to do that. So this integral is going to become, once I start plugging everyone in, the integral of 1 over secant squared theta times my dx is going to be secant squared theta d theta. These guys would cancel, and I would just have the integral of 1 d theta. Of course, the integral of 1 d theta is theta. And so since here my x is equal to tan theta, this means that my theta is equal to tan inverse. And so this is tan inverse of x. Right? So here, you realize that I could actually use trig sub to derive this new formula, tangent inverse, right? Pretty neat. And as you can see, that problem wasn't so long, but let's actually do another one. Let's do this last problem. And I'll leave the other examples for you guys to try for tomorrow, and then we'll hopefully go through those rapid fire tomorrow. Yeah, so for trig substitution, it'll depend. It was therapeutic. For trig substitution, it'll depend, right? So some problems are very long, they're very annoying, and the back substitution is annoying. Sometimes it's not. Whenever it's a definite integral, I definitely change the limits as opposed to back substituting, but there you go. Let's actually do this one. So at this point, I want you guys to help me with this one, and then I'll leave the other examples for you guys to try tonight, and then we can deal with them tomorrow. Okay, so go. What do we think here? So you can look back at your scans. So pretend you went through all the steps. Is this a basic rule? No. Can I simplify to look like a basic rule? No. Can it's regular substitution work? No. Integration by parts work? No. Okay. So let's say you settled on a trig substitution. What would you do here? X equals a secant theta. Be more specific. What is a? Right, a is square root of 3. Here, notice I can do x equals the square root of 3 secant theta, right? Because this looks like in the table x squared minus a squared, where if I take my a to be radical 3, then a squared is just 3. So this looks like x squared minus radical 3 squared. So my a is radical 3. And because I have x squared minus the number, the secant is the appropriate substitution. Therefore, I can do my derivative. Derivative of that is secant theta tangent theta. And now I'm going to actually plug these guys in. So I have 1 over x squared is 3 secant squared theta. The radical of this is going to be 3 secant squared theta minus 3 times my dx is going to be radical 3 secant theta tangent theta d theta. So here I just plug in. Okay. So that's our guy. So this is now the integral in the theta universe. Let's actually work it out. So here, This is 3 secant squared theta. Now 3 secant squared minus 3, I can factor out the 3. And that would just leave me with tangent squared, right? That's the whole point of doing the trig substitution here. With that, I can cancel the radical 3's. Then this is going to be a tangent squared under a radical, so that's just a tangent. So I can cancel the tangents. Then I can cancel the secant with that. So now, what does this actually look like? I can bring out the 1/3. This is going to be 1 over secant theta d theta. What's 1 over secant theta? How do I integrate that?
Cosine theta.
Right, just rewrite it as cosine theta. We know how to integrate cosine theta. That's just sine theta. All right, so that's the answer. That's the answer in terms of thetas. How do I get back to x's? Right, now since, remember our x was radical 3 secant theta, this means that x over radical 3 is equal to secant theta. This means my right triangle is like this. So this here is hypotenuse over adjacent. And so this is going to be the hypotenuse squared minus the adjacent squared. So this means that my sine theta is opposite over hypotenuse, SOHCAHTOA. So this is going to be x squared minus 3 over x. And so now I would just have that. So I have 1/3 x squared minus 3 over x. And that is my answer. Do we feel like we're getting it now? Any questions on that? So we saw this, couldn't really do that with any technique that we had before. So I think trig substitution, because I saw this part right here, the x squared minus 3, thinking of the 3 as radical 3 squared, I can come up with the appropriate trig substitution, find the dx once I find that, plug everyone in the integral, then this becomes a trig integral. Simplify that, and then do the trig integral. Once you do that, you are able to now find the answer in terms of thetas, and then using your original trig substitution, formulate a right triangle that allows you to rewrite all the trig functions in your answer back into x's. Yeah, which is why I asked you to use the screenshot from earlier when I asked you guys to take a screenshot. So it helps a lot to just have these things memorized. So that part in the table. Right. So far, I'm hearing that it kind of makes sense, except you just need a little bit more practice, which I agree. So we are essentially going to wrap up there, but what I will do is I will leave the rest of the examples I want to do in the notes. So these guys over here, I'm going to leave in the notes so you can see them and try them for next time.
Jhevon,
Yes.
I would like to talk to you like after class, like right now, or after
Okay.
class, like, you know,
Okay.
let you know.
All right.
Like,
I'll send you an email. Okay. So try these for next time, everyone. So try these for tomorrow. When I post the video in the PDF, I'll post these guys in there. But try to get through these. That will give you tons of practice. And we'll wrap up there. Okay, that's another one. Long day. We had our first quiz. Lots of things to learn from that. Remember that I have office hours the hour before class on Monday and Thursdays. Just send me an email when you want to meet for office hours for that in general. Yeah, so at the end of the week, I'll update you on quiz 2. But yeah, for the most part, you can expect the second quiz to be next week, Monday, at the beginning of class. All right, take care, everyone. Be safe. I'll see you guys in the next one.